Once again, you are welcome to Waidsum Academy. Today we are looking at nuclear physics, section 2 of nuclear physics, which is the radioactivity. So we're looking at radioactivity. So in that radioactivity, the first 2 chapter 5, part 2, section 1, we're looking at background radiation. So we start with background radiation. As fast as we can, let's quickly go through this topic. Okay, so when we say background radiation are actually radiations that are within us, in our environment. Okay, so when we say background radiation, we're referring to radiation that are all around us, radiation that exist around us all the time. The type of radiation that we have the normal radiation, but we have what we call the background radiation that exists within us. So it is very important for us to look at this background radiation, even if it contributes a little bit to the radiation in our environment. So even if it contributes a little bit to the radiation in our environment, so it's very important for us to look at this type of radiation. Now, radioactive elements have always existed on Earth and in space from time immemorial, from the very beginning of time. So we've always had radioactive elements. Okay, we always have radioactive elements like uranium, radium, thorium, and so on and so forth. A lot of these radioactive elements. So we've always had them in a very long while. Now, but human activity, these radioactive elements, they are natural. They are natural. They are not caused by us, right? But the human activity have increased the radiation that we have in our environment. For example, we say radiation are caused by the background radiation are caused by natural sources. Okay, this background radiation. So I will use the radiation for to quickly represent it. These radiations are caused by natural activities. Okay, they are caused by two phenomena. One is the natural activity, and the second one is the artificial or the man-made activities. So radiation or background radiations are caused by two critical phenomena: the human activity and the natural activity, the natural occurring phenomena. Okay, the natural occurring phenomena. So background radiation are coming from two dynamics. One is the natural concept, while the other one is the artificial concept. So one is the natural, the other one is man-made activities, human activities in our environment, like the burning of bushes, the breaking or smashing of rock, and so on and so forth. Okay, all these ones are our activity, or the tilling of the soil for agricultural purposes, all the constructions of roads and buildings. All these are man-made activities. So we have natural sources for our background radiation, and we have artificial sources for background radiation. So we have natural sources, which are like gases in the rocks, which are gases in the rock, gases in the soil. These are natural sources, earthquake, and so on and so forth. And then we have the man-made or artificial. So we can either say artificial or man-made. Artificial, like medical usage, like X-ray, using X-ray to find the imaging, to get image artificial. So these are artificial sources of radiation. Okay, artificial sources of radiation. So what the point we're trying to make, we have two sources of radiation, or two sources for background radiation. One is the natural, and the other one is the artificial one. Okay. Now, background radiation is defined as the radiation that exists all around us all the time. Radiation around us all the time. Radiation in our environment. When you sweep your house, the dust contains some background radiation. So this type of radiation that are all around us all the time, they are called the background radiation. A type of radiation that is always in our environment, always, no matter what you do, these radiation are all around us all the time. They are called background radiation. Okay. Okay, so now let's take a look at more extensively to this. Let's dive into this. Now we said there are two types of background radiation: the natural sources and the man-made source, or what we call the artificial sources. Now let's see the sources of background radiation. Where do we get them from? Usually, the most of background radiation comes from the radon gas. The radon gas that is emitted from the soil, okay, from the rocks under the ground, or the rocks on the soil. So this is the biggest. It contributes to about 50% of the source of background radiation, the radon gas. So I write the symbol. The symbol. Radon gas contributes to about 50% of background radiation in our environment. It contributes to about 50% of the background radiation in our environment. Okay, we also get background radiation from the cosmic ray. You know, cosmic ray they produce when they saw photos. When we say photos, we say quantums of light. Okay, when the sun's photo moving in the air hits air molecules. Okay, when they hit some air molecules, they release what we call the cosmic ray. And this cosmic ray form background radiation. Cosmic ray they contribute to 10% of background radiation. So when you say cosmic ray, 10%. Our food that we eat, 11%. So when we say cosmic ray, contribute to our background radiation, the radiation in our environment that we live with all the time. Okay? So cosmic ray contribute to about 10%. 10% of the background radiation that we have in our environment. Okay? Why the food? You know, when you grow food, the food itself, the process and the food itself, they contribute to background radiation. By 11% of background radiation comes from the food. Okay, when you mill rice, you know it has a husk, the one you have to remove. When you mill rice, the husk itself, they will contribute to background radiation. Right? So the food, the maize or the corn, when you remove them from their shaft, you contribute to background radiation. So the food we process, we make available, they add to our background radiation. So we're telling you the sources where we get it from. Medical, when you go for x-ray, they say go and take x-ray. Okay? Medical, more specifically x-ray. This one add to background radiation. So when you go for x-ray, when you take x-ray, you add to what we call the background radiation. Medical x-ray. Okay? You add to what we call background radiation. Right? Medical x-ray add to what we call the background radiation. Okay? So there are so many ways we add to background radiation. Okay? There are so many ways that we add to our background radiation. Medical x-ray is 30%. Rocks and building materials. The building material like the rocks, the gravel, all of these things, the cement, all of them, they contribute about 30%, okay, of our background radiation. So medical x-ray is 30%. Rocks and building material is about 50% contribution to the radiation we have in our background radiation that we have in our environment. So building material, rocks and building material. You know, we have stones. We use stones. We get stones from the rocks. Okay, when we blast rocks, we get stones. So we also get gravel. There's what we call gravel for building houses. We even get fine sand for building houses from the rocks. So all this one, they contribute about 15% of the radiation in our environment, of the background radiation in our environment. So we should know what is added to background radiation. And background radiation will always be there. Will always be in our environment, always, no matter what we do. Because we will continue to build houses. If you go to construction site, you get a lot of background radiation. We continue to build houses. We continue to build roads. We continue to build facilities, infrastructure. We continue to develop. So as long as you keep developing, you will keep having what we call the background radiation. Is that okay? You keep having what we call the background radiation. So all of building materials, okay, I just abbreviated the building. Rocks and building, not just building material. I'm talking about the gravel, the fine sand, the cement, whatever type of cement, all of this they contribute to background radiation. So when you open your cement, you see kind of is a bit dusty. Okay, those dust that it releases to the environment is the radiation that we're talking about. Okay. Okay, now let's move to the next one. What other material? I think these are. Then we have others, 1%. Others, others 1%. It could be a chemical reaction. It could be metabolic activity. It could be others. Any other thing that add to radiation in our environment, background radiation in our environment is just 1% of what is happening. Okay, of the total of its contribution to the background radiation in our environment. Background radiation are the radiation that are in our environment all the time. Radiations that are present in our environment at all times. They are called background radiation. Radiation that you actually not completely being able to do away with. They are called the background radiation. Background radiation is the radiation that is present all around in the environment. They are always present in the environment. A good example is the radon gas that is given off from some type of rocks. This radon gas is given off from rock underneath the ground, rocks from the soil. They give off radon gas and they contribute the biggest to our background radiation. They contribute to the biggest of the background radiation. Is that okay? So quickly let's move to the next one. Now, every second of the day there's some radiation coming from the natural sources. Every second of the day there's radiation that is coming from natural sources. We have radiation coming from the artificial sources or the man-made source, but let's take a look at the natural sources. Like for example, the rocks. The rocks, they emit radiation, background radiation every second of the day. So that's why we say these radiations, background radiations are radiation that are present in our environment all the time. Okay, so the rocks is one of the natural phenomena that is emitting background radiation into our environment. Another naturally occurring characteristics is the cosmic ray from the space coming from the sun. The collision of the photons, the quantum photo of light with the molecules in the air releases what we call the cosmic ray. And this cosmic ray, they are natural phenomena that are added to our background radiation. Another is the food. Another type of source that is causing our background radiation is the food that we eat or the food that we grow. When we grow corn, rice, whatever, wheat, whatever kind of crops or food we grow, we emit, in the process, we emit background radiation. Either in the process of harvesting, or in the process of planting, or in the process of processing the food. So we emit a lot of background radiation. Okay, but however, most background radiation, they are natural. They are not like, it's not all the time we are saying that they are caused by human. But human activities, they add small amount of it to the background radiation. So we are part of the problem. A good example is the medical procedures. Medical procedures, like the use of X-ray. Using the X-ray. X-ray add a lot of background radiation to our environment. Okay? That's why X-ray is not used all the time in our body, because it even adds some background radiation to our body. Okay? So levels of background radiation can vary significantly from place to place depending on where you are. If you are living near a construction site, you're going to get a lot of background radiation in your environment. Okay, if you're living when they're building the houses, you have a lot of dust, sound, noise, and dust, and all of these things in your environment. So background radiation varies from place to place, meaning it depends on where you live or where you are at a given point in time. So if you are in a place that is a garden, that is tied, no grass, no dust, then you will have less background radiation. Okay, unlike we go to developing countries like Africa, there's a lot of background radiation because they are still developing. There's a lot of use of cement, there's a lot of use of gravel, there's a lot of use of sand, there's a lot of use of the houses being built every now and then. There's a lot of road construction, there's a lot of all of these things. And a lot of road construction causes a lot of background radiation. So these are the natural sources, but the artificial sources when we start to, because those natural sources like the rocks, food, and cosmic ray is not our making. Okay, but when we start to make use of the natural things, like we're blasting the rocks, and we are getting gravel and fine sand and all the things, and we are manufacturing cement, we are causing environmental degradation. We are adding to the background radiation. So we should also find a way to clean up. So when you have a business or an enterprise that is engaged in blasting of the rocks and making sand, making fine sand, gravels, and manufacturing cement, then you are adding to background radiation. So you are polluting the environment. So you should also find a way to clean up the environment. Okay, levels of background radiation can vary significantly from place to place. We already established this fact. Now let's take a look at sources of background radiation. I think elementarily we've mentioned the sources of background radiation and we've itemized them with percentage. Okay, like radio gas in the air is the most one. It contributes about 50% of background radiation. Let's quickly rock through this because we've mentioned it. The airborne radio comes from the ground. Yeah. The radio gas comes from the ground, from the rocks underneath the ground. Now, this is from the natural decay of uranium in the rocks in the soil and the soil. Okay, so there is a rock. There are rocks underneath the ground, and also in the soil, we have when uranium that is found in the rock decay. When it decays, it releases radium and alpha particle. When uranium decay, okay, let's take a look at it. When there is a decay of uranium, okay, uranium, it could be any of the isotope of uranium, okay, it could be 235 or 238, whatever it is, okay, 238, let's say uranium 238, okay, so when it decays, maybe you blast it with anything, and it decays, it's going to give us a radon gas, right? Plus an alpha particle. So you can balance it up. An alpha particle can be represented with a helium nucleus. So when this happens, let's say here is 2, here is 4. Okay, so if you subtract 4 from here, you get 234. So here will be 234, and here will be 90. So you subtract 2 from, because of the alpha particle that has been released. So you subtract it from, you get 9. So this is a random gas. So when this happens, you see, when uranium in the soil or in the rocks, this uranium are found in the rocks underneath the ground, in the rocks. When they decay, you know, we've talked about decay last time. We say when the radioactive substance become unstable, you know, they're always unstable because of the high atomic number. Okay, when they become unstable, they begin to disintegrate. They begin to break into smaller units. They begin to disintegrate. So when that disintegration, breaking into smaller units is called decay. So when uranium in the rocks or in the soil begin to disintegrate or begin to decay, they will release what we call radiation, background radiation. This background radiation could be in form of alpha, beta, and gamma ray. We're going to talk about that. The cosmic ray is a gamma ray, okay? The gamma ray. It's when the light photon from the sun collides with air molecule, they release cosmic ray, which are called the gamma ray. So we also have alpha particle that is coming from uranium that disintegrate or decay to release an alpha particle. So there are 3 types of background radiation we're going to describe: the alpha particle, the beta particle, and the gamma ray. There are 3 types of background radiation, or 3 types of radiation that we will describe. Okay, but before we jump there, let's quickly look at what we're looking at. Is that okay? That will be coming in another section. Okay, it will be coming in another section: radiation, decay, ionizing power, types of radiation. It will be coming in 5.2.2 types of radiation. We talk about the alpha particle, the beta particle, and the gamma ray. They are the type of radiation that are emitted in our environment. And we talk about the sources of radiation detector. What the things that we use to detect radiation. Okay, the instruments that we use to detect radiation, that we use to find out how much radiation we have in our environment. Okay, so that's that for that. Let's take a look at, we were saying that when uranium decay in the soil, in the rocks, when they disintegrate or decay, they produce radon gas. This radon gas contributes to about 50% of the radiation in our environment, or of background radiation, not all the radiation. We're talking about the background radiation. This radon gas contributes about 50% of the background radiation in our environment. Okay? There are other radiation, apart from background radiation, there are natural huge radiation coming from nuclear power plants or coming from nuclear bomb and nuclear missiles and all of this. But we're talking about the radiation in our environment that lives with us. Okay, we're talking about the small amount of radiation that lives with us. And that small amount of radiation that is all the time in our environment is called background radiation. So that's what we're concentrating on. And the biggest contributor to this radiation in our environment is called the radon gas. 50% is contributed by radon gas to pollute our environment. Okay, so let's move on. So although the radon gas, we know what it is. It's tasteless and colorless and odorless, but it's not generally a health issue. Okay, it's not a big deal. It does not contribute big health problem or health decline. Okay, now let's take a look at another causes of background radiation: the rocks and the building materials. Okay, heavy radioactive elements such as uranium and thorium occur naturally in the rocks. Thorium also occurs in the rocks, not only uranium. Thorium, okay. Thorium occurs in the rock. When you blast thorium or when thorium decays, it produces polonium. Okay, produce polonium gas. Okay. So heavy radioactive element, they are found in the rock, in the soil. Okay, like uranium and thorium. They occur naturally in the rocks, in the soil, in the ground. Okay, in the ground. Rocks in the ground. Uranium decays to produce radon gas, which we've already established, and also emit an alpha particle. They have already established that with an equation. Okay, we've established that with an equation. We say uranium decays to produce a radon gas and alpha particle. This helium nucleus is used to represent an alpha particle. Okay, so that's for uranium. This is particularly dangerous if inhaled into the lungs. Now, when we inhale alpha particle into our lungs, it's going to, especially large quantity. In small quantity, we may still be fine. But when we inhale a lot of it, then we're going to have problems. We're going to have problems, okay? Cigarette also, all these cigarette smoke around us, they contribute to background radiation, okay? The natural radioactivity can be found in the building materials, like the decorative rocks. You know the rocks, when we build a house today, nowadays, we even make tiles. People are making tiles, we put tiles in our house. These are also contribute to background radiation. Decorative rocks. We put rocks on the body of the houses today, nowadays, and to decorate our houses. They contribute to background radiation in the process of blasting them, in the process of making them in the shape that you want to fit into the house. They contribute to background radiation. And even bricks, the bricks we use in building houses. When you are molding your blocks, in Africa we call them blocks. Here we call them small bricks. The small one is the bricks. So both the bricks and the blocks, when you mold them, you are contributing to background radiation. You are actually contributing to the background radiation in our environment. Okay? So there are so many things. So which means construction workers should wear nose masks, should wear the things to protect themselves from radiation. So when you're working in road construction industry or building construction industry, you should always cover your nose so that you do not inhale a lot of these alpha particles into your lungs. And when it becomes too much, you gradually kill yourself. Is that okay? Now let's go to another cause, the cosmic ray from the space. The sun, we say it emits an enormous number of photons. Photons means light. Photons and protons every second, okay? Some of these, they enter the Earth's atmosphere at very high speed. They travel with very high speed, and then they will collide with air molecules, right? And then it will lead to the production of gamma ray. So remember we talked about alpha particle, how it's being produced. We said that when uranium decay, it emits an alpha particle. It produces a radon gas and an alpha particle. Now, how do you produce the gamma ray? One of the way is when the cosmic ray, or when the sun emits protons and photons of light that travels through the atmosphere and collide with the air molecules, and this will produce what we call the gamma ray. Okay, this gamma ray, they are background radiation, okay? Now, other sources of the cosmic ray are supernova and other high energy cosmic events. Supernova and other high cosmic events. Is that okay? They all contribute to the background radiation. Then carbon-14, biological material. Carbon is very necessary in plants. The plants, they need carbon dioxide to make to photosynthesize. So they always take the carbon from the air. They always get carbon dioxide from the air. By so doing, they take carbon into their cells. Okay, carbon dioxide, there is carbon in carbon dioxide. So carbon-14 is always found in plants. So this organic matter contains a tiny amount of carbon-14, right? Every time organic matter that you get from the soil or from the air, they contain what we call the carbon-14. Living plants and animals constantly, they replace this carbon-14. Whenever it's being used, they always get it replaced. Okay, by so doing, it is contributing to background radiation. Now, radioactive materials in food and drinks. The food and drink we eat, radioactive materials are found there. Okay, naturally occurring radioactive elements can get into the food and the water since they are in contact with the rocks and soil containing these elements. So food and water, they grow in the soil, right? And the rocks are also in the soil. So sometimes the background radiation can even get into the food. That's why you have to wash and cook your food very well in order to reduce this radioactivity or background radiation that are found in these food substances. A good example is the banana. Banana, because they contain potassium, so this potassium, they deep-rooted and they obtain from the soil. So as a result, banana contains this a little bit of this background radiation. However, the amount of radioactive material is very small. It doesn't cause a big concern. The real radiation that is a big concern, they are huge events. They are huge events in the nuclear space, in the nuclear manufacturing space. Background radiations are in tiny amounts that really do not cause big harm or big concern, especially from the natural causes. Now let's talk about the man-made sources. The medical sources is number one man-made, where we get a lot of radiation. In medicine, radiation is utilized all the time. Although it has usefulness, we use radiation to do a lot of things, sterilization and so many other things. Okay, it has its own usefulness. So we use it in medicine all the time. Imagine the X-ray. We are using radiation to scan to get to the bones of the human body. So it's a usefulness. So we use this X-ray, CT scan. The CT scan to scan into our body also. The radioactive tracer in medicine and the radiation therapy. All of this is actually using radiation to benefit human beings. So we're using radiation to scan into our bone with the help of X-ray, using X-ray, we're using radiation, the gamma ray, okay? The CT scan also uses gamma ray to be able to penetrate the tissue. The radioactive tracer also uses the gamma ray to be able to penetrate the bones, the tissue, and so on and so forth, or leakages in pipes, leakages in oil pipes, to trace the leakages in oil pipes and other things. Okay, we are putting radiation into good use now. In this regard, we are putting radiation into good use. So when they ask you benefit of radiation, one usefulness of radiation, when they ask you about one usefulness of radiation, you should be able to start to tell, especially from the medical perspective. You say we can put radiation in use, such as X-ray, gamma ray, to scan into our body, into the bone. CT scan uses the ray, the gamma ray, or the X-ray, uses the gamma ray or X-ray to scan into our body. Okay, CT scan is a good example. Okay. Okay, so these are good uses. These are good uses that we can always bank on. Okay, for background radiation. Now, another sources of background radiation we are talking about the man-made now. Another source is the nuclear waste. The nuclear waste. Nuclear waste itself does not contribute much to background radiation, it can be dangerous for the people handling it. Okay, the people handling it, because it's super protected. They don't let it to escape to the environment. So it does not contribute much to the environment, but those who work there, they could be infected. Okay. Then another one is the nuclear fallout from nuclear weapons. And this one contributes a lot. The fallout is the residue radioactive material that is thrown into the air after a nuclear explosion. Like when the Hiroshima and Nagasaki bombing, when the United States, dropped a nuclear weapon or nuclear bomb in Hiroshima in Japan and Nagasaki in Japan, and they destroyed the entire two cities with just a nuclear bomb. Okay, so the whole place will ravage. The whole place will go into explosion. That's a nuclear fallout. The nuclear fallout is a huge issue. When there is a nuclear fallout, there is huge radiation, not just background radiation, but super nuclear radiation in the environment. The whole environment will be messed up. Every living thing, plants, animal, will be affected and will be condemned. We either die or paralyzed or destroyed in this regard. Okay, so nuclear fallout is a big deal, and is the residue that comes from a radioactive material that is thrown into the air, like in the case of you throwing a nuclear bomb into the air. So the residue, when the tea explodes, the boom and the smoke and the dust and everything is the nuclear fallout. Now let's go to another man-made source of radiation or background radiation, is the nuclear accident. Okay, when there is a nuclear accident, it may not be intentional. There is nuclear fallout, which is intentional. There is nuclear waste, which is the people working in the industry, in the factory, nuclear power plants, when they are exposed to these things. And then there is what we call nuclear accident, which is not intentional, like by mistake. So accidents such as the one in Chernobyl contributed to a large dose of radiation in the environment. Okay? Why these accidents are now extremely rare, we no longer get much of this type of accident, because we perfect the use of nuclear system, then the accident become reduced. They can be catastrophic and render area devastated for centuries. Okay? When these accidents occur, they can render the whole area completely destroyed. Now let's take a look at some exam tips. The sources that makes most significant contributions are the natural sources, like the radon gas, the rocks and building materials, food and drink, cosmic rays. They're the ones that make the most significant radiation. Okay, all these other man-made, they're little, because this nuclear accident no longer happens very much. There's no, since 1940 something during the Second World War or before the Second World War, since then we didn't use nuclear weapons. And the nuclear workers, they use so many protective gears to protect themselves. So the man-made ones are very little nowadays, but the natural ones are very significant. Now, how do we detect radiation? Let's move to another small subsection. How do we detect radiation, detecting radiation? We use counters, or what you call detectors. It is important to regulate the exposure of human beings to radiation, right? So in that note, we have to find something to detect the amount of background radiation that are in our environment. A machine that can help us detect how much radiation are in our given environment. Do you know when you sweep your house, when you sweep the floor, you actually contribute to background radiation, but you will still have to sweep anyway. So the dust is contributing to the background radiation. Okay, so that's what it is. It is what it is. Now the amount of radiation received by a person is called the dose. Amount of radiation that goes into your body is called a dose. It's called the dose. Okay, ionizing nuclear radiation is measured using what? A detector, or that is connected to a counter. Detectors and counter, they go hand in hand. The counter is to display what the detector machine has detected. The detector uses electrical impulses and electrical signal, and and display it as a number, a count number per second. Okay, a count number per second. That's what leads us to what we call the count rate. The count rate, because the detector detects the amount of radiation in our environment and detect it as a signal, electrical signal, in form of voltage or current, and transmit it and display it on the counter section of the connected system. Okay, so on the counter section you see the number per second. Okay, so and that is called the count rate. So count rate is the number of decays per second recorded by a detector and recorded by the counter or displayed by the counter. Now it's measured in count per second or count per minute depending on the machine. Now the count rate decreases the further the detector is away from the source, right? When the count rate decreases, then it means the detector is far away from the source. When the count rate increases, it means the detector is close to the source. When you bring a detector to your house or to your environment and you see a lot of high numbers, it means the radioactive source is very close to you. If the number is going down, as you move it around, it means you are getting farther away from the source, radioactive source. Okay? Now, let's take a look at those machines that we use as detectors and counters. Number one is the gigamolar tube. You need to know this. This is the IGCSE standard. We call it the GM tube. The GM tube, the gigamolar tube. So they will ask you to mention the three detectors we use to detect radiation. Gigamolar tube. This was a German scientist, okay, who developed a machine to detect the number of radiation in our environment. Okay? So we call it the GM tube. GM tube or gigamolar tube. Okay, this is number one detectors. This is number one. We're going to talk about that significantly. So detectors. You can say detectors and counter. Detectors and counters. Number one is gigamolar tube. We have scintillation chambers. Number two. Some places may just say chambers. We have photographic films. We have photographic to detect the amount of radiation in our environment. So these are machines or instruments to detect radiation in photographic films. Photographic films. Photographic films. We have scintillation chambers. Number three, we have scintillation chambers. We have scintillation chambers. We have ionization chambers. We have number four, we have ionization chambers. Okay, these are some of them, okay, but not limited to only this. We have what we call the ionization chambers. Ionization chambers. These are some radioactive detectors that helps to detect the amount of radiation or background radiation in our environment. Okay? But the GM tube is a very famous one in the exam. The GM tube is very famous radioactive detector, radiation detector. Okay, to detect the alpha, the beta, the gamma ray, this type of radiation detector are, so you can say radiation detector. They say radiation detectors. Okay, number one, GM tube. Number one, GM tube. Radiation detectors. Okay, so one we have a GM tube, photographic film, scintillation chamber, ionization chambers. Well, let's begin to look at them probably one after the other. Now here is a GM tube, okay? Here is a GM tube. This is a GM tube, a Giga-Muller tube, or what we call the Giga counter. It's a common type of radiation detector. Okay, so number one is like I say, this is a counter. You can see it displaying the whatever you have. This is the count. The detector part. So you can see this one is connected to electrical source, and then this is the mica windows. These are the mica windows that actually receive the radiation, amount of radiation, and then convert it to electrical signal, follow this place, and be displayed here in value, in counts. Okay, so this is a GM tube. Now, other sources are photographic film, which I have mentioned, ionization chamber, scintillation chamber, and also there's another one, the spark counter, scintillation counter. Okay, we can also call this one scintillation counter. Okay, /counter. /counter. Then number 5 is the spark counter, spark. So we've talked about 5, we'll talk about these 5. Okay, we already talked about a GM tube. We say it has a mica window, it collects radiation. These radiation are converted to voltages and current, and they be sent to the display counter, and the counter shows them in count per second. We're going to do some calculation about that. Okay, we have the spark counter. So you should be able to mention in the exam these types of radiation detectors. You should be able to tell us which instrument or machines can be used to detect radiation or background radiation in our environment. You should know them, you should be able to explain them, and so on and so forth. Okay, so that's that for that. So these are they are altogether about 5. Now before we move further, let's take a look at this question. Radioactivity, detection of radioactivity, detecting radiation, right? Now here is a question. Okay, and let's listen to this tutorial in order to move forward. Is that okay?
Here's a short question for us to look at, but we should nevertheless take a little bit of time to read through it carefully and make sure we understand what we have to do. From the list provided, identify which measuring device or devices can be used for detecting radiation. So we've been given nothing there, so it could be more than one of these 9 that we've been given can be used for detecting radiation. So this is simply an identify the measuring devices. So there are the keywords highlighted there. So there's nothing particularly funny in the question. Some of these may look familiar. Some of them may look a bit exotic. So the obvious one for measuring or detecting radiation, the Geiger counter or a Geiger tube, that's obviously not here. So we need to look at some of the other devices. So very simply, we just need to remember the names of the different devices. And as a reminder, these are the ones that are most often asked for. So photographic film, it says here in our theory, most often used in badges. That's typically people who are exposed to radiation on a regular basis have these badges, and over a certain amount, the badge or the film changes color, and they can then be removed from the source of radiation. There's the Geiger-Miller tube or the Geiger counter. You get an ionization chamber, a scintillation counter, and a spark counter. Now, the only one of these that appears on our list is the scintillation detector, so that is our correct answer. And I can assure you that the rest of these are genuine measuring devices, and if you are bored and have a bit of time in your hands, I would encourage you to go have a look at some of them. Some of them are actually quite amusing at what they're actually designed to measure.
Okay, so it was not a big deal. It was just talking about which of they listed a whole lot of measuring devices. They asked you which one to be used to measure radiation, and it was scintillation detector that was the one that was familiar. Okay, the one that was familiar was scintillation detection. Okay, the other ones were other measuring devices not for radiation. Okay, so that's it. The question can come in that manner. Now let's take a look at the mathematical question. A GM tube, a gigamolar tube, is used to detect radiation in a particular location. If its count is 60,000 decays in 1 hour, what is the count rate? If the count is 60,000 decay in 1 hour, scintillation. Let's end here. Scintillation. Okay, so he said, what's the count rate? Count rate is simply the count over time. Count rate, even from the formula, from the terminology, we can arrive at the formula. The count rate is simply the count per time, right? The count, that's the number of radiation. That's the count, number of radiation. So when I use number, I put NO, I put a small dash below it. Number of radiation over time taken for that measurement. Number of radiation detected, number of counts or radiation detected over time. But remember, the time will be in seconds. So the one they've told us 1 hour, we have to convert it to seconds. We have to change 1 hour to seconds over time. So this is count rate. Any T rate means divide by time. You know this from elementary physics or science, elementary science. So when we say rate, means we must divide that concept with time. Okay, so the count here, so we say number of radiation or count. I put bracket count. Okay, number of radiation or count that is present in the atmosphere or in our environment divided by time taken. That's what we call the count rate. So here the count is 1,600, or is it 1,000 or 60,000? Let's take a look. It says a gigamolar tube is used to detect radiation in a particular location. If the count is 60,000 decay in 1 hour, okay, 60,000. So the count is 60,000. So we're going to write 16,000. That's the count. We're going to write 16,000 counts over the time. Remember I said the time must be in seconds. So we're going to convert 1 hour to second. To convert 1 hour to 1 minute, we multiply by 60. Okay? To convert it to 1 minute, to convert it to minute, you multiply by 60. To convert it to second, you multiply by another 60. To convert it to second, you must multiply by 60 and 60. So from 1 hour to this thing will be 1 times 60 times 60. That will give us, this is time. Okay, time. This is time. This is what we're doing with the time. We're changing from hour to seconds. So this will become 3,600 seconds. This will become 3,000. If you multiply 6 times 6 is 36. Okay, this is how you do it with that calculator. Then you add the 2 zeros. That's 3,600. So 1 hour is actually 3,600 seconds. So we come here, we divide with 3,600. We divide with 3,600. If we're looking for count rate, you count the number of counts divided by the time it takes to make that count. The number of counts recorded by the device, by the radiation detector, or by the detecting device, over the time it takes to do that recording. So that's what it means, the count rate. So when you do this, then we will get, mathematically, we will get, when we divide 60,000 with 3,000, we get 4.5. So we get 4.5 decay per second. So when we do the division, you get 4.5, right? You get 4.5 decay per second. Because the count is actually decay. 4.5, you can say count per second, not only decay. You can say 4.5 counts per second. You can say 4.5 decay per second. Is that okay? So that's it. That's it. So for calculations like this is how you solve them. Don't worry, when we come to half-life, we also show you how to solve those type of questions. Okay? We also show you how to solve those type of questions. Now let's move on. Let's move on quickly. And then the next one, we've done this calculation. The next one is another exam tip. Okay, if you are asked to name a device for detecting radiation, the gigamolar tube is a good example that you give in the exam. Always don't leave out the gigamolar tube because it's very famous. Okay, so if you are asked to name a device for detecting radiation, the first thing that should come to your mind is to mention gigamolar tube, right? And then you can begin to mention, either if you don't remember gigamolar tube, say GM detector, or GM counter, or giga counter. Whichever way you say it, it's still okay. Is that okay? That should be the foremost in your mind before you measure all the other one, like photographic films, like you mentioned the scintillation counter, you mentioned the ionization chamber, you mentioned the spark counter, so on and so forth. Okay? All of this you add to it after that in case you are asked to measure more than one radioactive detector. Now, how do we account for background radiation? Accounting for background radiation. Background radiation must be accounted for when taking readings in the laboratory. We must account for them. Now, this is meaning how much we detected and how we make use of it, or how we clean the environment, or what we use it for, and so the recording, the usage, and everything. So this can be done by taking readings with no radioactive source present, and then subtracting this from the readings with the source present. So you have to take readings where there's no radioactive source, and you have to take readings when there's radioactive source, then you subtract them. You account for how many radiations are present. And this is called the corrected count rate. Okay? When you do this will be termed as the corrected count rate. Now let's see a question. In a laboratory, a detector of ionizing radiation detects an average background count rate of 8 counts per second. A radioactive source is now placed close to the detector, and the count rate on the detector increases to 200 counts per second. Okay, calculate the count rate due to the radiation from the radioactive source. So to calculate the count rate due to radiation, there's a count rate. The first one was it detects an average background count rate. So we always subtract the background count rate from the radioactive source. Okay, the background count rate, you have to subtract it from the radioactive source, or the radioactive count. The radioactive count is 200. The background is 8. So to get the actual radiation, you say, to determine the count rate of the radioactive source, if you're looking for only the count rate of the radioactive source, we must say 200 minus 8, which gives us 192 count per second. Okay? So we can listen to the tutorial to figure that out. Absolutely.
Here's a question for us to look at, and it's quite a wordy question, so let's just take a moment to read through it carefully and make sure we understand what is expected of us. In a laboratory, a detector of ionizing radiation detects an average background count rate of 8 counts per second. A radioactive source is now placed close to the detector, and the count rate on the detector increases to 200 counts per second. Calculate the count rate due to the radiation from the radioactive source alone. So let us make sure we know what we have to do here. So there's a calculation from the radioactive source alone. So we've got to take into account this concept of background radiation. And that's what we need to focus on here. What is background radiation? So just as a reminder, and just take a little bit of screen grab from the theory that we've been looking at, is background radiation is the radiation that is present all around in the environment. In other words, background radiation is all around us always. That level of radiation changes. It depends on the environment you're in. It depends what's near you. Bananas, for example, have quite a high background radiation, not enough to cause any health problems, but weirdly bananas are radioactive. Granite tops or granite countertops or any kind of granite is radioactive. There are a number of sources of naturally occurring radiation. What we need to do in this question is just take that into account. So what we simply do, and here's the step we're going to follow, is to determine the count rate from the source alone. We're just going to subtract the background radiation from it. And that's a relatively simple exercise. So we had 200 registered when the source was placed close to the detector. Without the source there, we had 8 counts per second, which means the source itself is producing 192 counts per second. So that is the amount of radiation coming from the source, taking the background radiation into account.
So that's it, which we have already explained. Here's another question for us. Okay, here's another question. A student, I think we're going to end with this section with this question. Okay, we're going to end this section with this question. And then our next one will be taking a look at the type of radiations that is emitted. Now, a student is using a GM tube, or what you call the Geiger counter, to measure the counts per minute at different distances from a source of radiation. Remember I said you can have count per minute or count per second, depending on the question. Okay, not count per hour. If it's count per hour, you have to either convert to seconds or to minutes. We say a student is using a Geiger counter to measure the count per minute at different distances from the source of radiation. Now their results and a graph of the results are shown below. Okay, the results and a graph of results are shown. The distance from the source. When the distance from the source was 0.2 meter, the count per minute was 180 counts per minute. When you go further away from the source, like 0.4 meter, the count rate dropped to 67. You know, the further away you move from the source, the less the radiation that will be detected. So 0.6, you got 29, 0.8, you got 17, 1.0 meter, that's 1 meter, you get 15. 1.2, you're still within 15. 1.4, you're still within 15. Okay, so determine the background radiation count. Determine the background radiation count. So the background radiation, you can see from this graph, the highest counts per minute is 200. And the highest radiation source is 180. So to find the background radiation, you will see that we can just subtract, right? We can just subtract and we'll be able to get our values. 200 minus 180, we'll get 20. Okay, we'll get 20. So take a look at the graph. Plotted this value at 0.2. No, 0.2 is somewhere here. If here is 0.5, here is 1.5. Because you can see these values, they are just in between from 0 to 1.5, you make a scale of that on the time axis. Okay, so here is 0.5, here is 0.1, here is 1.0, here is 1.5. So 0.2 is somewhere here, 0.25 is here. So 0.2 you take to 180, as in you take to 180 on the count per second, per minute. You put your point here. The next one is 0.4. 0.4 is close to 0.5. You bring it here because it's 67. Here is 67 if you look at the y-axis value. So the next one is 0.6, which is 29. So 29 is somewhere here, a little bit above half of 50. The next one is 0.8. 0.8 is 17. So you bring it here. The next one is 1.0, which is 15. You bring it here. And the next one is 1.2, which is also 15. Bring it here. And the next one is 1.4, close to 1.5, which is also 15. Bring it here. So you join all your points, you get this your graph. Using this table of values, so you get this your graph. Okay. Determine the background radiation count. Now let's take it to step 1. Determine the point at which the source radiation stopped being detected. The background radiation is the amount of radiation received all the time. When the source is moved back far enough, it is absorbed by the air before reaching the gigamillion tube, right? The result after 1 minute do not change. After 1 minute, the result remains as 1.5 and 15, 15, 15 count. Therefore, the amount after 1 meter is only due to background radiation. Okay, any amount you get after 1 meter, another way of doing this. After 1 meter, this is distance from the source in meter. Anything you get after 1 meter is due to the background radiation. So we can say the background radiation in this regard is 15. Okay, we can use this method and say the background radiation in this regard is 15. Because you see, after 1 meter, you keep getting a constant value, which means this is contributed by okay, this one was just a scale value. This is contributed by the background radiation. That's why the value becomes constant. Is that okay? Step 2, state the background radiation count. The background radiation count is 50 counts per minute. 50 counts per minute. So with this, we come to the end of this section. Our next class will be type of radiation. Today was background radiation. Our next class will be type of radiation. Type of radiation. Okay. After that, we'll go to ionizing power and deflection, and then we'll go to radioactive decay, half-life. So the next one will take these types of radiation and ionization power. We'll take them together, and then the other one will take radioactive decay and half-life together, and then the last one will take uses of radiation and danger of radiation together. Because background radiation is quite a lot, that's why we treated it only. So we have 2.22 and 2.23 together as our next one, and 2.24 and 2.25 as our next one. So with this, we've come to the end of today's class. Thank you for joining us.